Hello, in this video we're gonna see how we should solve this demonic looking integral from 0 to infinity of sine x over x. So there are many ways that we can do this integral, but the most common way is the Feynman's technique. So the Feynman's trick is a trick that we can differentiate a function under it, an integral. So how does this work? So you're gonna see, but generally we do introduce a new variable, and we try to remove the factor in our equation that causes our problem for differentiation. For example, here, x here is really the thing that stops us from being able to differentiate the thing here. What I'm gonna define a new function called f of t to be the integral from 0 to infinity of e to the negative tx sine x over x dx. Now, what I can do is I can differentiate f of t. It's going to be f prime of t, and I'm gonna take the derivative of the integral with respect to t of the whole thing here. So this d dt is gonna move inside, and it's gonna become a partial derivative. It's gonna be partial t. So my f prime of t is going to be integral from 0 to infinity of partial t of e to the negative tx sine x over x dx. Let me create more space for my future work here. I think that's enough, but anyways. Yeah. So it's sine x over x dx, and if we take the derivative of this e to the negative tx with respect to t, my f prime of t is going to be the integral from 0 to infinity of negative x e to the negative tx sine x over x dx. And these x's obviously are going to cancel out, and we got rid of the thing that did cause my a problem in differentiating and integrating this function. So it's going to be negative e to the negative tx sine x dx. So now here I'm going to recall a thing. Now that we're able to integrate this function, our goal actually here is to find f of 0, because f of 0, if you plug in f of 0, it's going to yield us sine x over x dx, because e to the power of 0 is just 1, and 1 multiplied by any number is that number itself. So if we have something like this, u dv, I can use the integration by parts, that is uv minus v du. So my u here is negative e to the negative tx, my dv is sine x, my v therefore would be negative cosine x, because if you take a derivative of negative cosine x, you're going to get sine x. So now the f prime of t is so my du is going to be t e to the negative tx dx. So this is my du here. So oops, what just happened here? Okay, sorry. So it's going to be negative e to the negative tx multiplied by negative cosine x, which these negative signs are going to cancel out. So the from 0 to infinity, we would differentiate it. Sorry, we would calculate its integral, and minus the integral from 0 to infinity of t e to the negative tx multiplied by should have been v du. So my v is negative cosine x multiplied by t e to the negative tx dx. So this negative is gonna make this whole thing here positive. So I'm gonna write f prime of t to be the e to the negative tx cosine x, the integral from 0 to infinity plus 0 to infinity of, so the t is constant, can be moved out, e to the negative tx cosine x dx. So now my f prime of t, if I calculate this limit, so e to the negative infinity cosine infinity minus cosine of 0 e to the 0, which is 1, which is going to go away. If you plug in cosine of 0, it's going to be 1, and e to the negative infinity is 0 because its approach e to the negative infinity is the same as e to the 1 over e to the infinity, which is 1 over a very large number which approaches 0. So this is going to go away, and only this term here remains, which is going to be negative 1 plus t, the integral from 0 to infinity of e to the negative tx cosine x dx. So I can again do a u substitution, integration by parts here again. So my u here again is e to the negative tx, my dv is cosine x, my v therefore is sine x. Okay, now my du is negative t e to the negative tx. Thus my f prime of t is negative 1 plus t, the whole thing, times e to the negative tx sine x from 0 to infinity minus the integral from 0 to infinity again of what do we have here? So it should be dv u dv. So sorry, v du. Sorry. So v is sine x and negative t e to the negative tx dx. So f prime of t here is negative 1 plus t times e to the negative tx sine x, the integral from 0 to infinity minus, plus, so t here again goes out, of the integral from 0 to infinity of e to the negative tx sine x dx. So now, think this thing here should be, this thing here should be negative, because so what did I do wrong here? U equals e to the negative tx, my du is negative t to the power of negative tx. Let's proceed further. Negative 1 plus t e to the negative tx. So this term here, again, the whole thing here is going to be 0 minus. So here, my bad. It should have been negative. So this thing is going to become positive. Okay, this thing is going to become positive t e to the negative tx sine x. So it's going to be plus t, the integral from 0 to infinity e to the negative tx sine x dx. Now, the whole thing here, e to the negative tx sine x, is equal to, so the 0 to infinity of e to the negative tx sine x dx is equal to negative of 0 to infinity of negative e to the negative tx sine x dx, which is negative f prime of t. That was why I got confused, because I'm teaching you this from, I'm solving this thing from my head. It should have been resulting in a negative here, which now it does make sense, because it should have been negative f prime of t. So now f prime of t is negative 1 plus t times negative f prime of t, because this is going to be 0, and this is going to be negative f prime of t. This whole integral here is going to be negative f prime of t. So f prime of t is negative 1 minus f prime of t. And if I collect the like terms, f prime of t plus t f prime of t is negative 1, and f prime of t thus is negative 1 over 1 plus t. And if I integrate both sides now, my f of t is going to be negative arc tan of t plus c, some constant of integration. So now I'm in the stage where I can find f of 0, but I first gotta find this constant of integration. So what I'm gonna do is I'm gonna equate arctan of t plus c to the original integral of mine, f of t, which was e to the negative tx sine x over x dx. And I'm gonna take a limit of both sides as t approaches infinity plus c, and equals to limits as t approaches infinity from 0 to infinity of e to the negative tx sine x over x dx. So as t approaches a very large number, this term here is going to go to 0, and as my t gets very large, as t gets very large, actually arctan of very large number is pi over 2. You can verify it graphically or with your calculator. So it's going to be negative pi over 2 plus c equals 0, thus c equals pi over 2. My constant of integration is pi over 2. So hold on, we were almost there. So my f of t is the integral, it's negative arc tan of t plus pi over 2, which is equal to the integral from 0 to infinity of e to the negative tx sine x over x dx. And if I plug in f0 for f, it's going to be, so arctan of 0 is 0, so pi over 2, which is going to be equal to the integral from 0 to infinity, e of negative infinity is 1, e to the power of negative infinity is 1, sorry, and the whole thing here, sorry, e to the power of 0 is 1, I got mixed it up. So e to the power of 0 is 1, which is going to yield sine x over x dx. Thus, our integral from 0 to infinity of sine x over x dx is an exact value of pi over 2. So that was how we could solve the this integral, this hard-looking integral with Feynman's technique, which is, in my opinion, the greatest integration technique of all time. It's very powerful tool. So thank you for watching this video. If you have any questions, please let me know in the comments. I'm gonna read all of your comments, every single one, and I will see you next video.